Calculation of dissociation constant through conductometric technique. So first of all, what is dissociation? Dissociation is solvation of salts in a solution, like separation of cations and anions of an electrolyte within the solvent. So there are two types of electrolytes known as strong and weak electrolytes. Strong electrolytes usually undergo complete ionization and therefore they have higher conductivity than the weak electrolytes, which undergo only partial ionization. For strong electrolytes such as salts, acids and strong bases, the molar conductivity depends only weakly on concentration. On dilution, there is a regular increase in the molar conductivity of strong electrolytes due to decrease in the solute-solute interaction. So in order to discuss the dissociation constant, so let's first discuss the Kohlraush law, which describes the non-linear relationship between the molar conductivities and the concentration of the electrolytes, which states that the molar conductance have inverse relation with the concentration. By increasing the concentration of the free ions concentration will be low. So by increasing concentration, free ion concentration will be low. Then the lower will be the dissociation. So according to this law, the relation between the molar conductivity and the concentration is given by this equation, in which lambda m is the molar conductivity having unit usually millisiemens meter square per mole. Lambda naught is the molar conductivity at infinite dilution. So I'm going to simplify this symbol that I have used in previous discussion. Lambda m infinity is the molar conductivity at infinite dilution. So I'm going to use this simplified symbol for this parameter, whereas K is the Kohlraush constant which depends mainly on the stoichiometry of the specific salt in solution. For example, for the case of sodium chloride, when it is dissolved in the water, it will be dissociated into sodium and chloride and having a stoichiometric ratio of 1:1. When sodium chloride is dissociated completely into sodium and chloride ion, then the concentration of the salt will be equal to its activity. Here A is activity and C is concentration, but actually there is another species, that is the ion pair. When this kind of species are present, then the activity is not equal to concentration, but it will be defined by the activity coefficient. So here, when the all species are ionized completely or dissociated completely, then the activity coefficient equal to 1. So here the ions which have been dissociated completely play important role in the conductivity and the conductance. At lower concentration near to infinite dilution, all of the ionic species are dissociated completely and they play a separate role in conductivity, whereas at higher concentration the ion pairs have been observed, making the ionic species unavailable, as due to increase in the concentration of the salt, free movement of these free ions is suppressed. That's why the molar conductance or the conductivity have inverse relationship with the concentration. Another important factor is the effect of temperature. At higher temperature, the free movement of the ions due to electric field gradient will be decreased at higher temperature. So the temperature also have inverse relation with the molar conductivity. So now let's come back to the activity of the dilute solution. At infinitely dilute solution, the activity coefficient is equal to 1. At that condition, the ion pairs are absent and all the ions are solvated and contribute their part in the conductance. So the total molar conductivity at infinite dilution is actually the sum of all the ionic species and their stoichiometric coefficients. For example, for the case of bismuth chloride, stoichiometric coefficients are 1 and 2, and in barium chloride, the conductivity of the barium +2 ion is 12.72 millisiemen per mole, whereas for the chloride it's 7.63. For this kind of salt, the molar conductivity at infinite dilution will be equal to the (27.98). This kind of calculation is used for the strong electrolyte, whereas for the weak electrolytes we need to measure the degree of dissociation. For example, if we have a weak acid like which is dissociated into hydronium ion and conjugate base in aqueous solution. So for this case, more the degree of dissociation, more will be the ionization. For this kind of dissociation, that is the dissociation of weak acid, we can write the equilibrium constant known as association constant, and it is actually the equilibrium constant. Now let's this weak acid is dissolved in water at initial stages when time is 0. The concentration of the acid was C, whereas the ionic species are 0, and at time T the concentration will be equal to activity, where alpha is the degree of dissociation and the concentration of the undissociated species will be equal to C minus alpha C. So according to variation in the concentration of the dissociated and undissociated species, we can rewrite the equilibrium constant as so now we have obtained an important constant, that is the equilibrium constant, which have been expressed in terms of degree of dissociation or the dissociation constant. So let's if we want to know that how much a salt have been ionized, so for this purpose we need to measure the value of dissociation constant. So according to above equation, dissociation constant can be derived from the equilibrium constant for the dissociation of weak electrolyte that is in equilibrium with the ionized and unionized species. We can rearrange this equation as now we can rearrange this equation in a form of quadratic equation, that is alpha square c plus alpha ka minus k a is equal to 0, in which a is equal to c, b is equal to Ka and C is equal to minus Ka. So using quadratic formula, that is alpha is equal to minus b 4ac minus b square over 2a. So according to this equation, we can rewrite this quadratic formula as minus Ka square root of minus 4c Ka minus Ka square, that is from here, over 2c. So now I have further simplified this equation. So here we can see that the second component of this side, that is the square root term over 2c, so we can take the whole square root by taking the square of this term. Here we can get 2c again if we take the square root of 4c square. Now we can resolve this LCM, minus Ka over 2c, that is plus minus 4c Ka over 4c square. Now we get the simplified term, so here the common terms can be cancelled, and this alpha value can be simplified as minus Ka over 2c, where C is the concentration, Ka is the equilibrium constant. So we have a simplified alpha relation that have been derived using the quadratic formula. So here we can take a common term, that is K alpha square over 4 C square. So here we have taken the term minus Ka square over 4 C square from here. So now let's take the positive part of the quadratic formula, that is minus Ka over 2c plus minus Ka square over 4c square, 4c over, here again we can take a common factor, that is Ka over 2c between these terms. That will lead to a final relation, that is Ka over 2c from here. The square root of Ka square over 4c square will be the common term, is Ka over 2c. So here for this term we have this common term is given here for the common factor Ka over 2c. So by using the negative part of the quadratic formula, we can get the final relation, that is 4c over Ka plus 1 square root minus 1. That is the acceptable relation that have been mostly used for the calculation of the dissociation constant. Using simplest dissociation of a weak electrolyte, we have mentioned the equilibrium constant, that was in terms of the dissociation constant was alpha square C over 1 minus alpha. So now again we can rearrange this relation as 1 over alpha is equal to 1 plus alpha C over Ka. Now this simplified relation can be obtained from the equilibrium constant as, at first I have rearranged this equation. Now keep 1 alpha in this left hand side, and now we have Ka minus alpha Ka over alpha C. After that resolve the LCM, that is Ka over alpha C plus K alpha K over alpha C, that is Ka over C, minus. Here we require 1 over alpha term, so it can be obtained from this term. So we need to rearrange this equation again, alpha plus Ka over C, that is equal to Ka over alpha C. So now we have this term, that is 1 over alpha equal to alpha plus Ka over C into C over Ka. Now open the brackets. 1 over alpha is equal to one plus alpha C over Ka, that is the required term. Here alpha is the degree of dissociation, which can be calculated using the conductometric technique, in which the alpha is actually equal to the molar conductivity over the conductivity at infinite dilution. So here we have conductivity at specific concentration over at infinite dilution. So now we are able to express this term in a form of conductivities. So here we have 1 over lambda naught is equal to 1 plus lambda naught C over equilibrium constant. By rearranging this equation, now we can get the term 1 over lambda, that is equal to 1 over So experimentally, now we are able to calculate the equilibrium constant using a relation given here known as Ostwald dilution law. For this kind of calculation, we need to vary the concentration of the solution. Then we will measure the conductivity of solution, then 1 over lambda, and a term that is C lambda C. So using a plot in which we will plot the values obtained from these two columns. So CA will be at x-axis and 1 over lambda on y-axis, and from the slope we can calculate the conductivity at infinite dilution, and from the slope we can get the value of equilibrium constant. And using this equilibrium constant, now we can calculate the value of alpha. So these two equations are used for the weak electrolytes, whereas for the case of strong electrolytes, another equation is used known as Shelousky equation. So in which F square is a constant that is obtained from the de Broglie rule, whereas S is another constant given as where Z is derived from the constant O conductivity at infinite dilution into concentration molar conductivity half, and here O is derived from where alpha is another constant equal to 8.2 10 to the power 5, whereas beta is equal to 82.5 over eta, that is the viscosity of the solution, into dielectric constant and temperature. Here D is dielectric constant. So here F square depends on the concentration and ion pairing. So for this purpose, if we have the values for the 1 over lambda s versus c lambda f square s, so from this plot, that should be a linear plot, we can calculate the value of Ka. Now let's consider an example of acetic acid. If the concentration is 0.01 mole per decimeter cube and its conductivity, that is the molar conductivity, is given at given temperature, and the conductivity at infinite dilution is also known, so can you calculate the association constant, that is the equilibrium constant? So here you can use the formula that is derived from the Ostwald dilution law, that is 1 over lambda is equal to 1 over lambda naught plus lambda c over and from this value of Ka we can also find out the value of pKa, that is the negative log of Ka. So in this lecture you have learned that we can calculate the dissociation constant and the equilibrium constant, that is Ka, using the conductometric calculations.